Everyone.
Okay, I'll introduce you. Welcome everyone to today's CDAC webinar. Hope everyone is doing well. I'm very pleased to introduce our speaker today, YbPt.P from the Department of Chemistry and Chemical Biology at Rutgers University. YbPt is a solid state materials chemist specializing in experimental and theoretical studies of quantum materials with a focus on new superconductors, semiconductors, and magnetic materials, including studies under pressure. YbPt received her bachelor's degree from Nankai University and then a PhD from Iowa State. She then was a postdoc at Princeton, where she worked with Bob Kava for 2 years and then moved to LSU as an assistant professor, going to Rutgers as an assistant professor a few years ago. YbPt has already received a number of honors and awards, including a Beckman Young Investigator Award, NSF Career Award, and a Rainmaker Emerging Scholar Award from LSU. And she's been really quite productive with some 133 papers already that she's published. So her talk today is, you can see, exploring novel quantum materials from chemistry perspectives. Welcome, and thank you for agreeing to give this talk.
Thank you, Professor Hemley. Thank you very much. And it's my great honor to give this talk to most of the high pressure people. Okay, so I will talk about how, as a chemist, and how we find the noble quantum materials. So, okay, let's get started from the first question. And people talking about quantum materials. So what kind of materials can call the quantum materials? Usually the materials show some very interesting and unique quantum properties which cannot be explained very well by current quantum mechanism. For example, superconductivity, right? So superconductivity in this system, the Cooper pairs can consider as the quantum entanglement system. So like quantum spin liquids and so on. So for me, what I am interested in is to making the new materials, which are superconductors, quantum spin liquids, and so on. But the most important things I like the most is the superconductor. And for the chemist, what I was always doing is I try to, so usually I have a physics question in mind. And then I try to think about some materials and using the chemistry way, like the structure, like the electron counting, chemical bonding, and these concepts. And then I translate this stuff, the physics, into the chemical requirements, like, okay, so what kind of structure like to host the superconductivity? What kind of the electron counting likes to host the superconductivity? And then we will do the inorganic synthesis to make the material and then to study the material. And we also try to understand the chemical bondings in the system. So overall, my goal is try to make new materials, which is never being reported in the database, and then try to find out some new materials can be applied for the immediately application. Okay, so in this talk, I will talk about 3 parts. The first part, I will just explain one example, how we find a completely new material from like the chemistry inspiration. And then I will talk about another 3 projects, what we are working on. Also like under the high pressure, but I want to talk about what's my motivation. So where my idea is coming from. Okay, so let's get started. So first of all, I think most of people know the superconductivity very well. Actually, superconductivity has been discovered more than 100 years. And superconductivity shows the magnetic levitations properties, that's the Mansley effect. And also superconductivity has 0 electrical resistivity. If we cool superconductor below the critical temperature, we will get the 0 resistivity. And also these days, people are talking about the superconducting material as the quantum material. It's because the Cooper pair in the systems is an ideal system to study the quantum entanglement. So yeah, so if we have time later, I can explain the interesting about the quantum entanglement. And however, there are not a lot of superconductor has been discovered. And the first superconductivity was discovered in 1911. And then after almost the half century, the first superconductivity, like convinced superconductivity theory was proposed. That's the famous BCS theory. And after almost 3 decades, the first high TC superconductor is discovered. And then after another 20 years, the second high TC superconducting family was discovered. That's the iron arsenic. So I think for the chemist, one thing we can do is, can we try to make more new superconductors so that people can, especially the high TC superconductors, and the people can understand the system better. So that's my goal. Okay. So one way for me to find a new superconductor is, okay, that's me. Okay, I'm not sure it's 100% true from the physics picture, but for me, when I'm looking for the new superconductors, I always consider the superconductivity, like the magnetism, like charge density wave, these interesting physical properties. A lot of time they're coming from the interesting, or I call it unstable electronic structure. So for example, let's take the superconductivity for example. Okay, so this is the equation we used to, the BCS, according to the BCS theory, this is the equation we used to predict the TC, right? And then for the conventional superconductor, if we want a TC higher, we have 2 ways. The first way is we make the W, it's the electron photon coupling, the vibration higher. And the other way is we make the density of states at the Fermi level higher. Okay, so making the electron photon coupling higher, one way we can do is try to use the light elements with the heavy elements. So then the vibration will be stronger. For example, lanthanum hydrogen, okay? So hydrogen is very light, lanthanum is very heavy, okay? So that's one way. And if we make the ambient pressure compounds, is we can try to put the boron into the system. And you can see here, I love use boron because once you use boron, the TC can go higher. And here also the boron stuff. And the second way we can do is to try to increase the density of states near the Fermi level. But if we increase the density of states in the Fermi level, there is a risk, is the compound may become not stable. So the goal is very simple, is try to make a compound, okay, has a very high density of states near the Fermi level, but at the same time, the structure can exist. So this is like one way I always use to find the new superconductor. I usually calculate the band structure and see if there is a flat band or very like saddle point, and then I will find the superconductor. Usually this is very practical, very easy way to find the new superconductors. And another way I'm going to talk about today is the new 115 superconducting family. So which I was inspired by the structure connections, not just the electron counting. So my original background is doing inorganic chemistry intermetallics. So one of my favorite compounds is the heavy fermion superconductor. Okay, so that's the cerium cobalt indium 5. So I like this compound very much. And then if as physics has different interpretations about the heavy fermion superconductor, but for me as a chemist, why I like this one very much is because this compound, we can consider it as a structure, a compound hosted the magnetism and superconductivity together. And which is very unusual because usually when superconductivity meet with the magnetism will kill the superconductivity immediately. So however, in this compound, the superconductivity survived. So then I was thinking, wow, that structure itself is very amazing. So if we can find some new materials which has the similar structure, can we find some new materials and very cool with very cool physics? So then the idea is also coming from the perovskite compounds with anti-perovskite compounds. So perovskite compounds, we know it always hosts, not always, a lot of perovskite compounds hosted the superconductivity. For example, potassium doped barium bismuth oxides, and the TC can go to the 30 Kelvin. This is almost the highest oxides without not cuprates. And then like the magnesium, copper, nickel 3, this is also, we call it anti-perovskite structure because the transition metal go to the oxygen side, and then the main group elements like carbon go to the inside. So we call it anti-perovskite side structure. And then, for example, strontium-3 tin oxygen, this is also a superconductor. So based on this one, I was wondering, can we find some like anti-115 structure type? So there is a one compound come to my mind. That's a magnesium, arsenic, platinum 5. But for chemistry, we like to write magnesium, platinum 5, arsenic. Okay, so it's similar but slightly different. Is the transition metal platinum will goes to the main group element site most, not exactly. And then the main group elements is like less. It's on arsenic only 1, but the transition metal will be 5. So this is like the anti-site. So in the beginning, we made this compound magnesium, platinum 5, arsenic. And then we do the superconductivity test below the 1.8 Kelvin. We go to the 0.1 Kelvin, and we didn't see any superconductivity. So then I say, okay, so how about this one? Can we change to another, like the other elements? So the first elements we try to find is like a small, a similar size, but also like magnesium usually is 2+. So we go to the magnesium is 2+. We go to the manganese, also always show the 2+. So we want to see if it has the magnetic properties. So then we find a new material, that's the rare earth free ferromagnetes. That's the manganese, platinum 5, arsenic. Okay, so we made these compounds. This is the chemistry lab, how to make the experiment. So we seal the tube, we put into the furnace and heat it. And then this is the compound we got. And we do the X-ray to study the structures and do the refinement to confirm the phase. And then we measure the properties. And it's a ferromagnetic, the transition temperature is at room temperature. And then we say, okay, that's cool, but our goal is to find out if there is any superconductivity. Okay, so for us is like you put a manganese into it and then you get something magnetic. So who is surprised, right? So then one thing we usually do is for the 115 phase, the heavy fermion phase actually is very sensitive to the C/A ratio. So if you press it a little bit, it can make it from the superconductivity to magnetic, from magnetic to superconductivity. So then one thing we did is we try to simulate, okay, if we press the unit cell, what will happen? And we find out for the manganese system, if we press it, okay, so the magnetic will change from ferromagnetic to anti-ferromagnetic, but we cannot find the superconductivity. And we studied the chromium, iron, chromium, manganese, iron, even cobalt, and we didn't find any superconductivity. So then we said, okay, so move to the rare earths. So rare earths, we also did the whole family rare earths, but we find a very interesting compound. That's the ytterbium, platinum 5, phosphor. So ytterbium is on the end of the rare earths, right? The last one is lutetium. So we can think about the ytterbium with the cerium as the opposite. So ytterbium need they have one hole, and cerium has 1 electrons, the F electrons. So they're quite similar from my view. And then we did the different ratios. So we find out this system is ytterbium. We can load the 0.25 ytterbium until like 100% of ytterbium into the system. So see here, we go from the 25% until to 100%, almost 100%. And then the magnetic property and the superconductivity property is completely different. So what we find out is if it's a fully 115, so ytterbium 1, platinum 5, and then phosphor 1. And what we got is this is the anti-ferromagnetic. And ytterbium shows the 3+, and it's a spin 1/2. And the transition temperature is very low. Okay, we measured it to 0.1 Kelvin. So this is the transition temperature is at the 0.3 Kelvin. However, if we measure the ytterbium low ratio, and the ytterbium will go to the only 0.25, like 25% ytterbium, and we see the superconducting transition very clear at 0.6 Kelvin. Okay, so So we think that's very cool. And then we try to think if this is the heavy fermion system. And however, we studied the band structure and we calculate the band. This band is, we didn't see the ytterbium contribute to the superconductivity. So it could just like, it's a conventional superconductor. It's not a magnetic intermediate superconductor. So it's different from the heavy fermion. But the thing is, we did the whole system from the holmium to the lutetium to the ytterbium to the yttrium, but only ytterbium we saw the superconductivity signal. So that makes me like kind of curious, because if we try to explain the superconductivity coming from the platinum with phosphor, it's like if for the ytterbium works, why for others it's not working? So it's not very convincing. But at that time, when the work is done, I still couldn't come up with a good explanation. But these days I have the idea, so I will talk about later. So how I came back the explanation about this system. Okay, so this work, so this is the story one. It's not about high pressure, and all this work is done by my graduate student Xingui, and now the graduate student Runway, with the help with my collaborator Martin, Tyrone, Gabby, and Huibo. Okay, so now let me move to the high pressure. So again, why I am interested in high pressure? Sorry. Sorry. Can you hear? Okay. Yeah. Okay. So sorry. Yeah. Okay. So now let's come into the high pressure work. So the reason for the high pressure is why I'm interested in high pressure is because the same, like I feel a lot of interesting properties can be induced under the high pressure. And for the high pressure, I'm interested in the two topics. The first question I want to answer from the high pressure study is, can we find more new phases under the high pressure, and which may be the superconductivity? And the second one is I try to see if we can use the high pressure to make the quantum spin liquid into the superconductivity, which will be very interesting because it will help me to understand the Professor Filippo Anderson's like RVB theory. So okay, so let's get started from our work. So the system is in the beginning, the system I get started is the trigonal 1 to 2 phase. So what we are interested in the trigonal 1 to 2 phase is because, so most of people study the tetragonal 1 to 2 phase, and like this, what I said is high TC superconductors, barium, iron, arsenic. But very few work has been done on the trigonal lattice parameters, this 1 to 2. Okay, and also for me is when I have any physics question, I like to go back to study our chemistry work. So one, I always study Professor Ro Hoffman's paper. So when I feel, okay, I don't have enough ideas, so I will look at his paper. And I also like to reading another professor, Professor Jeremy Burdett, the work. So that's I always read that paper, and every time I got a lot of inspiration from that work. So this idea is coming from the Professor Ro Hoffman and the Professor Zhen's work. Okay, they did the work in 1986 and 88 before I was born. So they studied the chemical bondings in the trigonal 1 to 2 phase. And they said, okay, the phase is very interesting because this trigonal 1 to 2 phase only exists in the D0, like the magnesium 2+, and the D5, like a manganese 2+, or the D10, like zinc 2+, this system. And if we look at the tetragonal in the system is, you find out the handle, it's like the umbrella. The handle is always like have the not the same distance from the trigonal structures. So when I read that part, I was thinking, okay, maybe we should test to use the high pressure to see what will happen. So what we did is, we starting from the strontium, manganese 2, phosphor 2. So because when I have an idea, I want to quickly to test it. So what I did is we just put it into the high pressure synthesis. So the high pressure multi-envelope system. And then we press it at 6 GPa, 900 degrees Celsius for half an hour. So just to see what will happen. And very, very interesting is after we treat it, after we treat it half an hour, and we find out the strontium, manganese 2, phosphor 2, it at the ambient pressure is the trigonal phase, but on a high pressure treatment, and it becomes the tetragonal phase. So after I did this experiment, I was like, oh yes, so that's so cool. So now we can study these systems, and then we think there will be a lot of interesting things will happen. So again, we starting from the similar compounds 1 to 2, but we use the calcium, manganese 2, bismuth 2. And when we, because doing this experiment is we do the high pressure synthesis. So that's to say it's stable at the ambient pressure after we treat it at high pressure, high temperature. But to be honest, in the beginning, I have no idea how much pressure do we need to make it like have a phase transition and so on. So we have to test it one by one. And what we did is we work on the high pressure X-ray diffraction, and then we find out where is the phase transition pressure. And it turns out we can clearly see the structure will change around the 2 to 3 GPa. And because we did the single crystal X-ray diffraction under the high pressure, so we can solve the crystal structure. So different from the high pressure, high temperature treatment, if we just use the high pressure at the room temperature treatment, we will not get the tetragonal phase, we will get the monoclinic phase. Okay, so this monoclinic phase, and we can see in general, so this is at ambient pressure phase, and you can see this is calcium layer and a manganese bismuth layer. And here, this is a high pressure phase. It's still like calcium layer, but then manganese and bismuth, so bismuth, manganese get much closer to each other. So they make this like the zigzag chain. Okay, so they like make the polyatomic systems. And after that, we did the high pressure, the resistivity measurement, because we try to understand what's the magnetic property changes in the system, or like is there any superconductivity. So we did the resistivity measurement, and we find out below the phase transition, below the structure phase transition under the high pressure, and the antiferromagnetic transition keep increase as we have the pressure, which is reasonable because we make their electrons get close to each other. And after the phase transition, one thing we find out is except the antiferromagnetic transition, we see another transition. Okay, this transition is as pressure goes higher, it decreases. So this is a little bit different. And then we didn't see any superconductivity in the system. So, okay. But if we want to understand what's exactly happened for this system, we have to do the neutron scattering, because this is a magnetic one. And my student's Madeline, and she is, okay, so she is really good. And what she did is she refined the structure of the magnetic structure, and which is measured under the neutron scattering. And then we figure out at the high pressure, the structure is not, the magnetic structure is not commensurate. Actually, it's incommensurate. It's like the conical structure, and which helps us to understand the system very well. And then the next things we are trying to do is, if we make this one, and we try to see, can we stabilize the phase, use the high pressure, high temperature synthesis. So Maddie also did a lot of work on this part, and one of the work just recently published. But so far, we made some like a bucked honeycomb system, we made some other system, but so far we didn't make any superconductivity from this system yet. So we will keep working, okay. Yes, so this is Maddie, And we also, Professor Antonio, Dr. Antonio at Oak Ridge also helped us a lot. So then only at the same time, okay, so Maddie and I was interested in another system. That's the strontium-2 iridium-04. So this system is very close. So people think this system is the closest system to the cuprates, lanthanum-2 copper oxygen 4. And however, if we look at the two structure comparison, okay, so here we made the comparison. This is the ambient pressure phase. This is for the cuprates. And you see, this is strontium-2 iridium-04 at the ambient pressure, the octahedral iridium oxygen octahedral oxides, and it's rotated oxides, and you can see here very clearly, right? And however, for cuprates, it's regular, so there is no rotation. And also there is and we see this is like the distance for the octahedral. It's like the ported. And then that makes us to think about, can we pressurize doing something to the strontium-2 iridium-04 on a high pressure, high temperature? And then what we can find out. So that's the idea coming from. And what we find out is we find a completely new strontium-2 iridium-04 phase. And this is non-centrosymmetric. So we made it under the high pressure, 1,400 degrees Celsius and 6 GPa. We just heated it for 4 hours. And this is a new phase we get. But it's, so you can see there is no octahedral rotation, but we have the oxygen splitting in the system, which is a little bit. Like later I will explain, we don't like that very much. Okay, so then this is a new phase we got. So here, now we make it in between. So this is ambient pressure reported. This is the high TC superconductor, and this is what we made under the high pressure, high temperature. And we can clearly see is now this rotation, we kind of fix it to the like the high TC superconductor, but still there are some problems. That's like the oxygen, we have the oxygen splitting. It's not fully occupied. And however, for the high TC, it's fully occupied. Okay, so then we measure the magnetizations and to understand what's going on, and especially if there is any superconductivity transition. So first of all, is compare with the ambient pressure strontium-2 iridates and the transition temperature of the strontium untreated on a high pressure. So this one, the antiferromagnetic transition decreased the 120 Kelvin. So that's a lot. So at ambient pressure, the transition temperature is 220, but here you can see it's around the 100 Kelvin. So that's a big difference. But the similar things is this one is still the mode insulator. Okay, and another difference is the magnetic moments for the high pressure treated strontium iridates is the moment is much larger compared to the ambient pressure one. So now what we are doing is, because like what I said is, okay, so then we did some calculations to confirm this is a mode insulator. And also we understand, so there is one question here is, no matter what kind of calculation we do for the system, no matter how big U parameter we add into the system, do the calculation, we still couldn't negate this is an insulator, but we do the calculation, you see here, it's an insulator. Okay, so then what we are trying to do is, we think it's the oxygen splitting really make, this is not the perfect material to make the superconductivity. So nowadays, what we are doing is try to see if we can dope the lanthanum into the system, dope the barium into the system, and then we also on a high pressure and see what will happen. Can we induce the superconductivity? So that's another high pressure work our group was doing. So, and like what I said in the beginning is when I think about doing high pressure, there is another interesting topic. The physics question I try to find out the answer is, can we make the quantum spin liquid or dope the quantum spin liquid or press it and make it a superconductor? Okay, again, so if we want to have a quantum spin liquid system to work on, and what I was thinking is we should try to make a new quantum liquid spin system, which can be like connected to some like a high pressure work, or like like what I did or what we did for the trigonal 1 to 2 phase is, if we want to find a system to work on under the high pressure, the first things for me to do is we need to make sure it's like some interesting or exhaustive, like the very unique physical properties can be induced, because we don't want to do a lot of work, but then the result is not very exciting. It's always exciting, but not very exciting. So find out a system to work on is very critical. So again, when I have some physics questions, I always go to the chemistry papers. So I read a very interesting paper by Professor Roy Hoffman. He also wrote it in the 1980s about Kagumi lattice. So the first paragraph he said is Kagumi lattice. So when for the physics people study the Kagumi, they always say, oh, Kagumi is in a quantum spin liquid and so on and so on and so on. But the first paragraph Professor Roy Hoffman wrote is Kagumi lattice we can consider as the planetary pattern in the lattice phase. And when I saw that, I got very exciting, because lattice phase is, we can connect the lattice phase with the spinel, with the perchloride structure. So then I was thinking, wow, that's a good point to start. So can we connect the Kagumi lattice with the lattice phase and with the spinels compounds? So then another compounds we are, so then another reference we are reading is the 112. This is A is the alkylic metal and the lanthanum group elements and oxygen. So they find out there are a lot of different structures in the system. If we change from the lithium to sodium, potassium, rubidium, cerium, and the structure will make a big change. So that means that's indicate is chemical pressure really is, so this system is very sensitive to the chemical pressure. So you change the compounds larger, smaller, the structure change. So then based on this one, so recently people work a lot on the sodium, ytterbium, selenium 2. And the sodium, ytterbium, selenium 2 is in the perfect regular triangular lattice. It's in the rhombohedra. So then what I was thinking is, how about we work on the lithium one first? So, and it's kind of like, for me, I feel not surprised. Okay, so we find that it's in a cubic structure type. It's a new pyrochlore lattice. So this is the crystal structure. Okay, so this is the crystal we grow. So we can grow very big crystals. And then we find out ytterbiums is in this lattice. Okay, it's very interesting. So now we made it. So after we made this one, that's not my like final goal, right? My final goal is I want to see if we can make it a superconductor. So this one you can see it's a typical insulator, and it's transparent purple color. So it's not even metal, so it's not superconductor. So what we did is we work with our collaborator and the Dr. Jing Guang at the Chinese Academy of Science Institute of Physics. So I say, hey, Jing Guang, I give you an interesting compound. Can you press it? So then he start press it. So after he pressed to 25 GPa, he told me, hey, wait, we haven't seen the resistivity yet. I said, okay, then you keep press. Okay. So he keep pressing until to the almost 100 GPa. And then he starts seeing the superconducting signal at the 94 GPa. So then the diamond was broken. I said, okay, so we can keep press, because the idea we were thinking is for the quantum spin liquid. And as we keep press, the band gap will close, and then some flat band will come and the superconductivity will appear. So we will keep doing this work. Yeah. Okay. So this is some of the experiment they did under the high pressure, and you can clearly see it becomes from the transparent to the metal color. Okay. Okay, so this work is done by my graduate student Ranuri, and then Haojie, and then our collaborator at the IOP. So yeah, so this is all of my talk. And do you have any questions?
Thank you very much for a very nice talk. It's beautiful data.
Yeah, I just talk about what we are doing right now because I want to see if we can collaborate with more people to explore the new materials together.
Right. Well, I think your chemical approach to these problems resonates with a lot of people in the audience. So the session is open now for comments and questions. Just unmute yourself or put your questions or comments in the chat box or raise your hand. Maybe I'll start with some technical questions. You mentioned the diamond cell work at very high pressure earlier, but you are also using a different kind of presses for the synthesis. You're using Walker type presses, I guess. So what was the maximum pressure you could go to in those synthesis experiments?
So synthesis experiment is, we can go to 8 GPa. So that's for sure. But most of the time is we go to 6 GPa. Yeah. So yeah, this is our goal. Our goal is try to make the material as easy as possible. And because we are not developed the technique, special technique like the high pressure people was doing. So we try to see if like an easy access, like can make the new material. That would be awesome.
And in the neutron scattering work, what kind of device were you using?
Oh, so that one we use this like the what's that? That's called the Paris, like the press, Edinburgh, Paris.
The PE cell, right? Paris
Yes.
cell, right?
Yes.
Okay. Okay. Go ahead. YbPt.P, would you like to ask a question? I see your hand is raised.
Can you hear me?
Oh, yes, go ahead.
Okay. I need to switch the microphone. So about the Pyrochlore system, so what kind of order inside? Is that very similar property like ytterbium 227 Pyrochlore?
No, it's different. It's completely different. Okay, so first of all is in the 227 system, it always shows the very strong magnetic and isotropic. But this one, we also measure the magnetization from the different directions. It's very, there is no magnetic and isotropic, it's magnetic isotropic.
Oh, awesome. Okay.
Yes. So that's why it's very interesting.
And any magnetic order?
No magnetic order. We measured down to 0.07 Kelvin, and we didn't see any magnetic order.
Very interesting. Does it? One more question. Does it like a? Oh yeah. Is it stable at like a ambient? Is this like a sensitive or like a stable?
No. Yeah, it's
Not
very stable. It's
very
very
stable.
stable.
Okay.
Yeah, very, very stable.
Okay, I'll talk to you later. Yeah. Thank you. Very nice. Yeah.
Okay, thanks. You made a number of references to Rold's work, and he has a question or comment. Go ahead, Rold.
Hi, Wei.
Hi.
It's good to see you. Thank you for the references to our work. I'm glad you continue to find it interesting. Something about the strategy that I wanted to mention. So in the compounds which Bob Kava has explored of the iron selenite type with the thorium chromium 2 Si2 structure, that's you know very well.
Yes.
Somehow I've had the feeling that though we were not smart enough to predict superconductivity in that system, that it is somehow that the crucial phonon is somehow tied to the bond being formed, for instance, in that structure. And that is what attracted Chong, Zhang, and me initially, that there were some compounds in which there were like phosphorus 3-, and then there were some compounds in which the phosphorus was oxidized from to allow the formation of a Pp bond. So this connects up to some other things that I've sometimes thought about the superconductors and about even the cuprates, that there is a valence instability or a valence transition where there is an oxidation reduction that is connected to bond formation. And there is something like that in some of the high pressure structures where some systems which are unsymmetrical at high pressure become symmetrical. So for instance, we know that for water at high pressures about the hydrogen bond, we begin to see H3 units in some hydrides. And I've wondered if this would not be a place to look for the superconductors with or without pressure. That is, look for systems where two structures are related by the formation of a bond between two of the atoms. Because I think that is what was the essence of the thorium-chromium-2 Si2 system, that it allowed that bond formation. So I just wanted to mention that as an idea for possibly thinking about potential superconductors until the time that we have a more chemical theory of these things, which we don't have yet.
I think I kind of get your idea, because one thing we are looking for these days is this called the local structure. And I don't know if it's a little bit related to what you're talking about, because I also, because recently we find another new compounds is the similar, is they are the same thing, the structure, everything is the same. If we do XRD, the structure is the same. But however, their property is completely different. And the magnetic ordering is completely different. And then just like what you mentioned about the iron selenium, so we said, okay, why not? We look at the local structure to see if the atoms, they really like, it's not like they are the same, like X-ray, just see the average electron distribution. So if we can see the local structure and everything, so maybe it will give us a better understanding. So that's what I am working on these days, like doing the neutron and the X-ray, the PDF study.
Yes.
Yeah, so we try to see if we can also do that under the high pressure. So that's, yes, but
Yeah.
but that's interesting because I think, yeah, that's very cool. Thank you.
Okay, keep up the good work.
I will keep working hard.
I have a very quick question.
Yeah.
Sure. You made some connection between unstable structures and superconductor. It's
Yes.
I think I totally agree with you that most of the high TC structures that we have seen, usually they have sometimes unstable mode. That's at least within the harmonic approximation, they have imaginary frequency, but including the harmonicity became. So is there any critical studies to elaborate that make this connection between high TC and unstable mode? Or
I think the system, well, not really, But what I try to interpret, or like I think maybe the Professor Philip Anderson's like RVB theory is kind of this kind of things is, well, I try to interpret in this way. It's not I don't know what he really think about that one, because when people was also talking about this like saddle points in the system, in the band, I think what they want to say, even flat band theory now is very popular. It's all about, because it's a flat band, and then there are some like the critical points where it happens at the Fermi level. And it's not necessary to be superconductivity. It could be like charge density wave. So this is one method we always use. So like also my experience, just like Professor Roy Hoffman said, we feel, okay, so when I try to make new superconductor, I always try to look at the system like a semiconductor. We try to dope the semiconductor, or charge density wave, we try to quench the charge density wave. Like I said, okay, we shake it a little bit, and then charge density wave will disappear and the superconductivity will come out. Or we use like the dope, the anti-ferromagnetic mode insulator, right? So we kill the anti-ferromagnetism and induce the superconductivity. So yeah, so I think, I don't know if people really studied this one and made it into the theory, but that's really what we are doing all the time. Yeah.
Thank you.
I think, Sabri, I believe what you're describing is in fact the case for a lot of the hydride superconductors within a conventional BCS theory. That is, you get this instability of the at low frequencies and very strong electron-proton coupling.
Yes. So for example, H3S, they have it. Lithium hydride, they have it. So I think at least the most high TCs, they have such things.
That's right. That's right. Okay, Nilesh, do you have a question or comment?
Yeah, I have a question actually. My question is regarding the high pressure superconductivity observed in lithium LiYbSe2. You observe the superconductivity at very high pressure, around 90 GP or so. So did you see any structural transition in between?
Yes, 10 GPa.
Okay. So that 10 GPa structure continues all the way to 90 GPa, which is actually the superconducting. It's not the ambient structure. Okay.
Yes.
Yeah.
Okay, thanks.
Okay. Yeah.
More questions or comments?
And you are very welcome to send me email and ask for samples.
I guess I have a question. Maybe you covered this in the strontium iridate. How high in pressure have people gone to look for the insulator metal transition? You talked about the persistence of the Mott insulator phase. How far does that persist in pressure?
So that part, I think people already studied, just like non-high pressure synthesis. They always go to, I remember there is a paper go to 45 GPa.
And the Mott insulator phase persists?
No, but they also didn't see superconductivity.
Oh, okay. But it is metallic at those
Yeah.
points. Yeah, okay. Any more comments or questions? If not, thank you very much, Wei.
Thank you.
Talk. Thank you for giving it, and thank you all for joining us.
Okay. Bye-bye.
Thank you.